Hello. In this video, we are going to take the integration formulas that we derived in the previous video that determine the centroid, or the center of mass, of a planar region. And we're going to apply those formulas to calculate the centroids of a few examples that I have chosen that you can see down here at the bottom of the screen. We will look at a rectangle, a triangle, a semicircle, and this region that is underneath part of a parabola. You can pause the video and visit this Desmos URL that I have there. And if you do that, it will pull up this set of Desmos graphs that I will keep toggling back and forth between while I record this video. And you can change between the various examples by turning on and off a folder. So for example, at the top left of the screen, you see there's rectangle, and right next to it there's a little folder icon. If I tap that, it disappears. If I tap it again, it comes back on. And I can turn that one off and turn on the next example, the triangle, and then the semicircle, and the parabola, and so on. And if you so choose, you could even click the arrow that's right next to the word rectangle to expand that folder to see all of the tools in Desmos that I use to graph that specific region and label that point. And you could do that for the others just to get some insight into how to use Desmos yourself. So again, here are those formulas that we found. If I have a region in the plane bounded between the x-axis and the graph of some function, y equals f of x, so in the rectangle example, that's going to be the top line. For the triangle, it's that one. For the semicircle, it's that one. For the parabola, it's going to be that graph. And between some bounds, x equals a and x equals b. So in the rectangle example, those are the left and right boundaries here and here. For the triangle, it's those. For the semicircle, it's those -2 and +2. And for the parabola example we're going to get into later, it's going to be between 0 and 2. We'll do some algebra to figure those out. Then the centroid, the center of mass of that region, has x and y coordinates given by these two integration formulas down here that we derived in the previous video. Let's start applying these to some examples. First, let's consider the rectangular region bounded below the graph of f of x equals 2. That is the function that we're talking about, and its graph is that upper horizontal line we see in the graph there. And we're going to go between x equals -2 and x equals +2. Those are telling me the left and right boundaries of the region. And without even knowing those integration formulas, I hope you would agree that it makes sense that the center of mass, the centroid of this rectangle, is exactly where you might expect it to be. It's right in the perfect geometric center. It's right at the midpoint of the rectangle. So in this case, it ranges from y equals 0 up to y equals 2, so it should make sense that the centroid is halfway up at y equals 1. And the region ranges from x equals -2 all the way over to x equals +2, so it makes sense that the centroid is right in the center there at x equals 0. So a couple of things we'll need to do. Notice that both of those formulas for x bar and y bar, the coordinates of the centroid, they both involve 1 over a, where a is the area of the region. So the first step we're going to do in all these examples is to figure out the area of the region we're talking about first. Now in this first example, I have just a nice rectangle, so there's not really much to do there. I just have to do the width times the height of that rectangle. The width is from -2 over to +2, so that's a width of 4. And the height is from 0 up to 2, and that's 2. So I have a total area of 8. I don't need to do any integration or anything crazy to find that. To calculate the x-coordinate of the centroid, I'm going to set up and evaluate this integral. So I have the formula pasted here from the previous slide. 1 over a, the area is 1 over 8. I'm going to set up an integral from the far left side, x equals -2, all the way over to x equals +2 on the far right-hand side. And the formula says x times f of x. X times, in this case, 2. That's the function f of x that I have highlighted already over here. That's where that 2 is there. That's f of x. And this is a pretty simple integral to evaluate. I have 1 over 8. Antiderivative of x times 2, or in other words, 2x. The antiderivative of that is x squared. And I'm going to evaluate between -2 and +2. And there I've written out some of the steps. I have 1/8, and I'm going to plug in the upper limit of 2 and then the lower limit of -2 and subtract their outputs. That's what the fundamental theorem of calculus tells us. And in this case, 2 squared is 4. -2 squared is also 4. And so what I get after all that is 0. Now that also shouldn't be shocking because, as I said before, this rectangle is perfectly symmetric across the y-axis, so it should make sense that its centroid, its center of mass, is sitting there at x equals 0. It's on the y-axis. So getting a 0 out of this is not surprising. Let's figure out what the height, the y-coordinate of that centroid should be. So I'm going to go to the y-bar formula down here. I'm going to have 1 over 8 from the area. I'm going to have an integral from, now here when it says AB, that still is the same limits on the x. I know we're finding a y-coordinate in this example now, but this is still asking about an integral with respect to dx. So I'm not thinking about the y-coordinates of the region when I'm setting this up. All of these integrals are still in terms of x. And so that's why I'm still going to have an integral from -2 to +2. But in this case, the integrand, the function inside, is going to be 1/2 of f of x, which is 2, all squared. So that 2 there, that's again the f of x function that we're dealing with all along. And so that's a nice simple integral, even easier than the other one because this is just an integral of from -2 to 2. Inside I have 2 squared is 4 divided by 2, it's 2. So I don't even need to write out any antiderivative here. I can just say this is asking for the area under the graph of 2 from -2 to 2. So that's a width of 4, a height of 2. 4 times 2 is 8, all over 8. That's 1. And there I can see I got 0, 1. That's exactly the coordinates of the centroid point right there. Next, let's look at this triangular region. Try to make sure that you would be able to figure out for yourself, even if I gave you this graph, you should be able to come up with the fact that this is under the graph of f of x equals 2 minus x from x equals 0 to x equals 2. That's something you should be able to do on your own. And then you may even want to pause the video now and try to apply these formulas for yourself and make sure you come up with the same result that we're going to, that the centroid, the center of mass of this region, is 2/3 of the way along the x-axis, and along the y-axis it ends up being at 2/3, 2/3. So why don't you try that on your own for now, and then I'll show you the details here written out. Okay, let's do that together. The area of the region is something I will need because that's the A in those two formulas down below. So let's do that first. Still, I don't need any integration here. I know that the area of a triangle is 1/2 base times height, which in this case is 1/2. The base is 2, 0 to 2. The height is also 2. So in this case, the area is exactly 2. So when I start evaluating this x bar integral down here, I'm going to have 1 over 2. That's the area that we just calculated here. I'm going to have an integral from 0 to 2. Those are the boundaries that I see here in x. I'm doing an integral with respect to x. And the function itself is 2 minus x, so there's x times the function. I would recommend distributing that x into both parts here. I get 1/2 of this integral from -2 to 2 of 2x minus x squared. So I get 1/2 antiderivatives now. 2x becomes x squared. X squared becomes 1/3 x cubed. I'm going to plug in from -2 to 2. And oops, I hope you caught my typo there. I'm integrating from x equals 0 to 2. So then when I plug in, according to the fundamental theorem of calculus, the upper limit of 2 and the lower limit of 0, I get those values that you see over there. And all of that evaluates to, let's see, 1/2 of 4, that's 12 thirds, minus 8 thirds, that's 4 thirds. So I get 1/2 of 4 thirds, or 2 thirds, which is what I told us the answer was going to be. Let's apply the y bar formula, the calculation of the y coordinate of the centroid. I still have 1 over the area, which is 2. And I'm going to do times an integral. Again, like the last slide I mentioned, I'm still doing this all with respect to x. I'm going to integrate from 0 to 2. That's because it's the left and right boundaries, the x coordinates. I know in this example the y range is also 0 to 2, but that's just a coincidence here. I have 1/2 of the whole function, 2 minus x squared dx. I'm going to do two things at once here. I'm going to take that 1/2 and pull it out in front of the integral. So I have a 1/4 out there instead. And then I have an integral from 0 to 2. And then I'm just going to expand this square. I'm going to see 4 minus 4x plus x squared. Make sure you get the same thing after doing some algebra. And then I'm going to scroll down to make some more space and write an antiderivative. There's that antiderivative. And I'm going to start plugging in the lower and upper boundaries of 0 and 2. But in this case, when I plug in the upper boundary of 2, I get 4 times 2 is 8. 2 squared is 4, double that is 8. 2 cubed is 8, so I'm going to get 8 over 3. And then when I plug in 0, the lower limit for x, I'm just going to get a bunch of zeros everywhere, so I don't even have to worry about that. I'll just write it like this. And then all of that cancels nicely, and I get 8 thirds over 4, or 2 thirds. Again, that's what I expected. That's what I told us the answer was going to be. Next example, let's look at a semicircle. Now, for this example, I've chosen a specific radius of r equals 2. In the class notes that I have shared with my students, I have the same problem written out with a generic r for the radius instead of a specific 2. But after we do this example here on the notes right now, I'll show you how to generalize what we've done to obtain a more general result for any circle with any radius. Let's do the same stuff. I need to find the area of this region first. I know that the area of a circle is pi r squared, and I'm only looking at the top half of the circle, so I have 1/2 of that. In this case, r is 2, and 2 squared is 4, half of that is 2, so I have a circle with area 2 pi, a semicircle, I should say, with area 2 pi. Now, to calculate the x-coordinate of the centroid, let's do that now. I have 1 over the area. That's where this 1 over 2 pi is coming from. I have an integral from -2 over on the left to +2 over on the right. Those are the a and b values that I'm going to put in here. And then I have x times f of x, the square root part. And then to evaluate this antiderivative, I'm going to make a substitution. I'm going to substitute w to be 4 minus x squared, the entire quantity underneath the square root. The reason for doing that is its derivative is -2x, and that's not exactly what I see. Notice here I have in the integrand an x dx, and I do have that appearing here as part of my dw term. The only difference, the only thing that I have to account for is that multiple of -2. So let me write this substitution derivative in a slightly different way. It says -1/2 of dw. That's exactly that x times dx that I'm going to account for. So where I see that x dx in the original integral over here, I'm going to replace that with -1/2 of dw. And there I've started to do that. You can see the negative 1/2 dw that I've replaced. I have now written root w because I chose the quantity underneath the square root to be exactly my w in the substitution that I'm making. And the only thing left I have to account for are the boundaries, the limits on the integral. If x ranges from -2 to 2, what's the corresponding range of values for w? Well, think of it this way. Originally, x was ranging from -2 to +2, and I chose w to be 4 minus x squared. So let's take each of those x values on the boundaries from -2 to +2 and plug in those in for x here to see what the corresponding w would be. Well, if x is 2, 4 minus 2 squared is 0, and therefore w would be 0. So that's going to be the upper boundary on my new integral that has everything in terms of w, not x anymore. And if x is -2, and I plug that in here, I get 4 minus -2 squared is 4 again, so I get another 0. And so this is going to be an integral from 0 to 0. Well, hey, I don't even care what the integrand is. That's a region with no area, has no width. And so I find 0. But you know what? I don't think I even needed to do all this. I didn't need to do all this integration. Perhaps this is a good reminder and refresher and practice with integration by substitution. But still, I feel like you should be able to look at this region, see that it is symmetric across the y-axis, and therefore state without any integration, the centroid, the center of mass of this region, must be on the y-axis, where x equals 0, because it's symmetric across that vertical line. So for my students, in the context of an exam question, let's say, you wouldn't necessarily need to write out all of this integration work for me. You could just write in words what I just said out loud. This region is symmetric across the y-axis. The centroid must be on the y-axis. And that would be a perfectly acceptable answer for me. But now, the interesting part, why is the y-coordinate of that centroid, why is that this mystical 8/3 pi here? Where is that coming from? Let's calculate that now. At least the pi shouldn't be too surprising because I have 1 over the area, and there's a pi in the area. But I wonder where that 8/3 is coming from. Let's start to write this out. And here I've decided that I need a little more space, so I've just started a new page. I've rewritten the integration formula we're about to apply, and I've started to plug in the information that we have from our problem. Here's the a and the b ranging from -2 to 2. Remember that I know we're calculating a y-coordinate now, but everything is still in terms of dx, so that's why I'm thinking about the range of x values of the region. And I've plugged in for our specific function f of x, that square root of 4 minus x squared that defines the upper boundary of the semicircle. And so, although this may look crazy or annoying for an integrand, this actually isn't so bad to integrate because the square root and the square perfectly cancel each other out nicely. And then I just thought of this, another thing I could do is that 1/2, I can pull that out in front and therefore write 1 over 4 pi integral from -2 to 2, and the 4, oops, there's the square root squared is just 4 minus x squared itself. And then I can start taking an antiderivative. 4x minus 1/3 x cubed from -2 to 2. And then let's plug in that 2 as the upper boundary and -2 as the lower boundary and see what we get. Notice I get the exact same numbers in the green and the red there, but opposite signs. So all of this is going to be 1 over 4 pi times, well, I have something minus the negative of itself. So I could also write that as 2 times that green quantity of 8 minus 8/3, which is 24/3 minus 8/3. So 16/3. And therefore, let's see, 2 times 16 is 32. All over 4 is 8. That's where I'm seeing the 8 over 3 pi. And looking back on the previous slide, that's exactly what I said the answer was going to be. Pi is a little bit bigger than 3, so that denominator is a little bit bigger than 9. So this is 8 over 9 point something, so it's a little bit less than 1. And if you jump over to the Desmos tool and put on the semicircle, you can see the decimal version of that 8 over 3 pi quantity is indeed a little bit less than 1. Now think about it this way. The region ranges from y equals 0 up to y equals 2. So if this was a perfect rectangle, the center of mass would be right in the middle at y equals 1, just like the first example we did. Why is this center of mass a little bit lower? Why is the y-coordinate a little bit less than 1? Well, look at how the region is much wider and fatter at the bottom as opposed to much narrower, much thinner at the top. So more of the mass is concentrated towards the bottom, towards the x-axis, the horizontal axis. And therefore, it's not surprising. I would have expected this centroid, this center of mass, to be lower down the y-axis, below 1. And I can see that coming out from our calculations. So what about this would change if I change the radius from 2 to something else? If I make it, 5 or 10 or what the heck, let's say an arbitrary r and use that letter, for example. Well, all of the boundaries on my integrals are going to go from negative r to r. And instead of 4, I'm going to see r squared. So if I want to change this to an arbitrary radius, I only have to change a couple of things. That would be the radius squared there. This would be from negative r to positive r. And it wouldn't affect the calculation of x bar, the x-coordinate of the center of mass. That would still be 0. I would still see something symmetric across the y-axis. And down here, it would affect some of the numbers that come out of this evaluation. And so I'll just write up here in the top right, you can check by plugging in these things for yourself and making sure that you get this. In general, for any radius r, not just the specific radius of 2 that we did in this example, for any arbitrary radius r, the y-coordinate, the centroid, will turn out to be 4r over 3 pi. So you can see how in our example, r being 2 led to this 8 over 3 pi. Make sure that you can replicate these calculations with that arbitrary r written in instead of specific numbers, and that you find the same result. Okay, here's another example. Let's find the centroid of this parabolic region, this region bounded underneath a parabola, the graph of a quadratic function. And I've said here from x equals 0 to x equals 2 as part of the setup of the problem. I could have also phrased this as find the centroid of this parabolic region in the first quadrant. And I would trust that you know that that means in the top right over here, so you'd know that x equals 0 is one of the boundaries. And maybe you'd have to do a little bit of algebra to find the x-intercept of this function, to find that it's x equals 2. Just factor that quadratic equation and find its roots. They're negative 1 and positive 2. So you could do a little bit of algebra to come up with this same information if we needed to. Now for the area of the region, this is something where I don't have a nice formula for from geometry like we had for rectangle, triangle, or semicircle. So for this one, I'm actually going to have to set up and evaluate some kind of integral, this case from x equals 0 to 2, of the function itself. That's going to be what tells me the area of the region. There's the antiderivative of that function. I'm going to plug in the lower limit of 0 and the upper limit of 2. When I plug in the upper limit of 2, I get 4 plus 1/2 of 2 squared is 2. 1/3 of 2 cubed is 8/3. And then when I plug in the lower limit of 0, I get 0 squared, 0 cubed, blah, blah, blah. I get a big fat goose egg out of all that. So let's see, 4 plus 2 is 6. 6 is 18/3. So minus 8 is going to give me 10/3. That's the area of this region. That's what I'm going to eventually plug in over here and here. So just to keep things nice for now, I'm going to keep writing 1 over a as we do some calculations, and I'll plug in those numbers at the end. So for the x-coordinate of this centroid, I'm going to get 1 over a, integral as x ranges from 0 to 2. Now I'm going to do something at once here. I'm going to say x times f of x. Let's distribute that x into the 3 terms of this function f of x. So without writing out that detail, I hope you'll see what I'm doing here. I'm just going to multiply each of those terms by x. And then I'll take an antiderivative and start plugging in the lower 0 and the upper 2. There's that antiderivative. And I can say now this is going to be 1 over a times, and as before, if I plug in the lower limit of 0, I'm going to get a 0 out of everything, so I'm just going to plug in the upper limit of 2. 2 squared is 4. 2 cubed is 8 thirds. 2 to the 4th is 16. 16 over 4 is 4. So after all that, I get 4 minus 4, those disappear. So I get 8 thirds. Remember, 1 over a was 10 thirds. All that times 8 thirds. Dividing by that fraction is like multiplying by its reciprocal. So I get 3 over 10 times 8 over 3. Very nicely, those 3's disappear. And I get 8 over 10, or 4/5. And that's what the x-coordinate of the centroid is. I'm going to open up a new page to make sure we have enough space to do the y-coordinate calculation. Now let's see. The y-coordinate is 1 over a, the integral from 0 to 2. Again, I know this is a y-coordinate calculation, but this is still an integral with respect to dx. So I'm going to write everything in terms of x. I have 1/2 of, and then here's f itself. I'm going to have all of that squared. So let's do something here. I can take that 1/2 and pull that out in front. So I'm really going to see 1 over 2a out in front. I'm going to see an integral from 0 to 2, and then I have to do a little bit of algebra writing here to do that thing squared. And here's how I like to think of that. I have 2 plus x minus x squared. All of that squared means all of that times itself. And I'm really just going to apply the distributive property a bunch of times. So that initial 2 on the left factor, I have to multiply through to all 3 of the things on the right. So I have 2 times 2 plus 2 times x minus 2 times x squared. And then I have to take that x term and distribute it to each of the 3 things in the factor on the right. So I'm going to have x times 2 plus x times x plus x times negative x squared. There's that. And then finally I have that negative x squared distributed through to each of the 3 things over there. So I have negative x squared times 2, negative x squared times x, and negative x squared times negative x cubed. So there's a positive, negative x times negative x squared. So there's a positive x to the 4th. And then I have to combine some like terms here. So here's what I like to do. Let's see, I see an x to the 4th. So I like to underline that 4 times. I don't see any other 4th powers. I see an x cubed and another one. So I'm going to underline those 3 times, and I'm going to put them together. I see a couple of x squareds and one more. I see a couple of x's, and then I see a lone 4. So after all that, I have 4. I have 2x plus 2x, negative 2x squared. Negative 2x squared is negative 4 of them, plus an x squared, so I end up with negative 3 of them. Where are my cubes at? I got negative 2 of them. And I got that lone x to the 4th at the end. So this is how I like to organize and conceptualize all of this algebra. I haven't memorized a FOIL thing. I don't really like that phrase. I'm just doing the distributive property over and over and over. It doesn't matter that I have 3 terms in this one. I have a trinomial instead of 2 terms, a binomial. It's still the distributive property. And if you have the advantage of color coding things, I like to do that here so I know that I have the 3 terms for each of the 3 distributive property applications I'm doing. And then this underlining helps me keep track of combining like terms so I know I haven't missed anything and I haven't double counted anything. So after all that, I've got 4 plus 4x minus 3x squared minus 2x cubed plus x to the 4th dx. And I'm just going to open up one more page, make sure we have enough space to actually evaluate that integral. There, I've pasted it in. And now I can say this is 1 over 2a. Antiderivative is going to be 4x, 2x squared minus x cubed, 1/2 x to the 4th, 1/5 x to the 5th. I'm going to evaluate this from 0 at the bottom, x equals 0, to x equals 2 at the top. And as keeps happening in all these examples, when I plug in that 2, I'm going to get a bunch of numbers. But when I plug in that 0, I'm going to get nothing. So I'm just going to see what happens when I plug in the 2. 8. 2 squared is 4, doubled is 8. X cubed is 8. Wow, 8's out the wazoo. 16 is 2 to the 4th divided by 2. Oh my gosh, another 8. 2 to the 5th is 32, all over 5. And let's cancel till our heart's content here. 8 plus 8 minus 8 minus another 8. So, oh boy, 1 over 2a. A was 3/10, so I'm going to say 3/5. That's 2a. A was 3/10, that's the area of the region, so I'm going to have 1 over 3/5 times, after all that, 32/5. And so dividing by a fraction is like multiplying by its reciprocal. And oh gosh, I hope you caught my little mistake here. Area wasn't 3/10, it was 10/3. So let me clean that up really quickly. There we go, that looks a little more like it. Sorry about that. So I have 1 over 20/3, so reciprocal, that's 3 over 20 times 32 over 5. You may notice that this 32 in the top is 4 times 8. That 20 in the bottom is 4 times 5. So I can cancel out their, let's see, their multiples of 4. So I'm going to get in the top 3 times 8, and in the bottom 5 times 5. And that's 24 over 25. And phew, after all that, there is the result that I was expecting, that 24 over 25, or 0.96. Okay, one final example here, just to show you that it's possible to generalize those formulas to a planar region like the one you see down here that's not bounded between a curve and the x-axis, y equals 0, but bounded between two curves, the graph of a function f and the graph of a function g. You can see here I've restated those integration formulas, but you can notice the difference between what we had in the other formulas before and what we have here. Now I have f of x minus g of x, and here I have the same thing with f of x squared minus g of x squared. And the only difference between these and the ones on the very first slide are that the ones on the first slide were for a situation where the second function was a constant 0 because it was bounded between a curve and the x-axis where y equals 0. So if I plug in g of x equals 0 into these two places, I would recover the same formulas we had earlier. And just for your practice, I have an example down here of a region bounded between two curves. I have a quadratic function and a linear function. As before, I have a link to Desmos, so if you pull that up, you will see a graph of that region. Oops, sorry, this one. And you can use that to check your work by clicking on and seeing the intersection points. For example, I would trust you can do some algebra to solve for those 2 points. You can also kind of see what I'm doing on the formulas on the left there to calculate things and graph things. So if you want to kind of teach yourself Desmos, the application as well, you can do that. And I will recommend that you start trying to solve this problem on your own. Do some algebra to discover those intersection points here and here, by setting these two functions equal to each other. Then start applying these formulas that I have up on the top and making sure that you get the results here. You might want to pause the video and start going about doing that. And I will skip ahead to the later slides, which just have those answers. And so you can pause the videos on those to compare to what you've been working out on paper. So here now is some algebra to solve for the intersection points. You can see they happen at x equals -1 and x equals 2. I need to know those now because those are going to tell me the lower and upper limits on any integrals we're doing. So the area of the region is x goes from -1 to +2. And why am I doing f minus g in that particular order? Because over here, f is the curve that's on top and g is the curve that's underneath. So I'm going to subtract f minus g in that order. And that's how I get the area here. You can pause the video now to compare your work to these steps that I've written out, typed on the slides. And then finally, here are the calculations of the integrals for finding the x-coordinate of the centroid and the y-coordinates of the centroid. And so you could just compare your work to whatever you're doing on paper, make sure you get the same results.